All right, let's kick off a little earlier than usual. Here, there we go. Man, that is some poor lighting. Hello, everyone. Let me pull out my magic coat hanger stick. There's the decent lighting. There we go. Hello, hello. Let me make myself big. Actually, no, that'll ruin the chat. Oh well, whatever, I'll stay small. Hello! So, welcome to what is effectively our last content lecture in 6991, I think. So, we have, we still have week 10 and there's still lectures set during week 10, but there's no, accessible scheduled content. So I'm still trying to decide, what we should do with week 10. One thing I can mention is that when we were, still in very much the planning phase of the course, we've still been planning the course over the year or two before the start of term, and Sebastian Sequoia Grayson, who UNSW very smartly snatched up, gave a very nice piece of advice when I was chatting to him one time about 6991. He said, make sure you have absolutely no scheduled content in week 10 in case everything goes horribly wrong and things start running overtime and all that. And fortunately, I believe we've made it to, well, I guess we've almost made it to week 10, and we haven't totally crashed and burnt, and so we're actually in the good case here, where it turns out maybe we don't have too much to worry about next week. This is also going to be our last week of weekly exercises. So the weekly exercises have been released. They were released a little late. I mentioned in Monday's lecture that Shrey has now disappeared overseas, excuse me, and he was usually in charge of the weekly exercises, so Tom and I ended up picking up some of the work there, but it's now all ready. We've got 3 exercises for you this week. Rust to C, which is about calling a secret C function from within Rust. Unsound unsafe, which is about a broken unsafe program that has some undefined behavior in it, which you're meant to patch up. And then myRC, where you actually get to make the RC type yourself, which is also pretty cool. Now, because we were a little late in releasing them, usually they come out Sunday night, Monday night, something around then. We don't really anticipate many students end up doing much exercise work on, say, the Monday, Tuesday, or even Wednesday, really, just because we usually haven't covered all the content necessary. So hopefully it doesn't disrupt your usual flow and plans too much, but as a bit of a courtesy, we have extended the deadline by a day. I have mentioned that I have no real problem with changing this to be week 10 Friday as well, adding another day onto that. But again, we've usually found that students prefer to have very separate, distinct deadlines for assignments and weekly exercises and that sort of stuff. So this is just what we opted for. We can't do a weekend or a Monday deadline, sadly, but if you would strongly prefer this to be a Friday deadline instead, I'm happy to extend that. So just make your voice heard on the forum. I think there is even a post on the forum currently about this, which I believe is extending the deadline till Friday or Saturday. We can't do Saturday again, but if you agree with this, if you want to see the deadline on Friday, just maybe give this post a heart, or reply with any of the thoughts that you have. And if there's significant support, I'm happy to bump that to Friday as well. So we're talking about 2 things today. I think this is going to be a really fun lecture, if I'm honest. We're talking about 2 things, which is finishing unsafe that we were talking about on Monday, and then also talking about foreign function interfaces, or FFI. And it's going to be like a bit of a... I think it's going to be a bit of a psycho mode lecture. Psycho mode in that we're going to be writing like some pretty psychotic code. some pretty maybe slightly egregious, dangerous code, which is, it's always fun where there's some risk and some, some unsafety involved. And we will absolutely take some shortcuts in some places to make the lecture fit and all that. And it's going to be pretty fun. Things will probably go wrong. I'm relatively excited for this one. So we're going to start off where we left off with unsafe, which is trying to create a sometimes usually sound vec, which is basically to say, like, I'm not 100% certain that this is going to be... So I am certain that there's going to be unsoundness in certain cases. I think I'm reasonably confident that in the usual cases it should be sound, like what we write should end up being sound, but I would be more than happy to be shown or proven wrong. And so I think we're really just going to be having fun with it. And yeah, just really playing around. So, another quick note. I mentioned last week that the primary tool for testing unsafe code, unsafe Rust code, is Miri, the Rust mid-level intermediate representation interpreter, which basically interprets over your Rust code and looks for naughty things. I did, after a lot of pain and suffering, I did manage to get Miri installed on CSE. So you should be able to run 6991 cargo plus nightly Miri run, like this, essentially. So Miri is a nightly only tool, because it uses a lot of unstable Rust features. So you need to tell it to run on the nightly channel, and then you should just have access to Miri run. And this, I would, if you're working at home, I'd suggest installing Miri yourself, which usually looks something like rust up plus nightly component add Miri, something like that. And you should be able to run Miri then at home yourself. But running Miri on CSE is also now a possibility. Also, some of the auto tests run Miri, so the unsound unsafe runs your code with Miri to try and check that the undefined behavior is fixed. It might actually be sensible to run the MyRC auto tests with Miri as well, now that I think about it. But I don't believe they do yet, because I ended up it was a real big escapade getting Miri working in auto test as well. So I might actually update the RC exercise potentially after the lecture to use Miri as well, because that seems to make a lot of sense. Maybe running it even just both normally and with Miri might be a good idea. Anyway, let's write some psycho code. So our idea is that we'd like to make sort of like a minimum viable vec. So we should be pretty familiar with vec at this point. In the sense of we have our list, we can push things, we can pop things, we can get things at an index, something like, all this kind of stuff. In terms of what we'd like to write ourselves, well, let's do cargo new lib. Let's call it, I'm going to call it vec insane, because we're just sort of going insane with it. And it's not really, I'm not expecting us to take this, as absolute gospel. It's more like this is, me doing, mostly my best here. And I'm probably going to get some things wrong, and that's okay. We're writing a bit of like slightly insane code. I guess we'll keep this. We'll get rid of that. Okay, and so we'd like to make some kind of like MyVec of T. And what would we like to see on, like, what would we like our API to support? Well, we're definitely going to be able to need to be able to make a new vec. So pub for new goes to a vec. We definitely want that. What else should we support? Because we're not going to write all these functions, to be clear. That would be seriously insane. What's pretty important? I guess push push is pretty important, so we'll want to write that. Pubfin push at mute self value is some t to do. And if we're implementing push, I think it sort of makes semantic sense to also implement pop, which basically just removes the last element from a vector and gives it back, right? And if the vector is empty, then it returns none instead. So pubfin pop at mute self, and that gives us an option of a t to do. What else is pretty important? Probably like getting the like get method. Get me an element at blah index. The alphabet is hard. Oh right, and they get in this case from a trait implementation, which would be index. I believe get comes from. Does get come from index? Am I crazy? I think it does. Index. Yeah. No? I mean, we can find it. Vec get. Oh, slice. Oh, of course, I'm silly. It's coming from a slice. So a vec, you can, when you do like vec.blah, it implicitly can dereference into a slice, and then the slice will, okay, so we'll just implement get ourselves. So we'll have a pubfin get, takes a shared borrow of self and an index, which is going to be some index into the vec, and that should give back some option of a t. Okay, so let's say this is the API we'd like to create, but we don't want to just like do this by going like, you know, take someone's already written, you know, vec and then just use vec inside. We want to actually pretend as if we were making vec ourselves here is the big idea. What are you upset about? Oh, okay. Not using t yet. That's fine. Great. So, I mean, we can start with a test as well. Now, like we've got our API surface, so we should be able to write some sort of a test like pubfin, oh, sorry, not pub, just like a function, it works, is fine by me. And we'll just say something like let mute vec equals MyVec new. We'll say vec.push hello world. You know, this is COMP6991, and then we'll just say like for I in 0 to 10, something like that. Print out the debug representation of vec.get of that index I. So we've done new, we've done push, we've done get, we haven't done pop. So maybe vec.pop. And I guess it makes sense to print out anything that we pop. I'll just say like pop this, like that. Pop 3 things off, and then maybe just do this whole index loop again. And I mean, this is not a particularly good test, to be clear. Not a particularly good test at all, because it's not actually testing anything really, apart from the absence of panics. Instead, it's just like it ends up printing stuff out. But like, I'm fine with that in principle, just to sort of help us, just to help us see our how our vec is working, if it's doing the right thing. Okay, so we've got our little test case ready to go, but right now it's just going to immediately break because we haven't written MyVec. So, how should we implement a vec? I guess it's a good point to, oops, it's a good point to probably hop onto a drawing tablet and think about what a vec might look like. So we have MyVec of t. So like, how should we end up structuring something like this? So we should probably start by saying like, laying down some principles in that a vec is very dynamic. If we just stored like, you know, values is like a t here, that'd really be no good, because like when we're sort of storing something in line here, right, without using a box, without using malloc and free essentially, we can only store like a fixed amount of these values. So even if we use something like an array, like we'd have to write a number in here, you know, 4096 T's or something like that. And we have to store exactly 4096 T's. So that's really not going to work for us. Instead, we're going to need something like a pointer to some box allocated memory or something like that, just memory that's been allocated for us that can grow and shrink over time. So we might start off by saying we have like 4 elements, you know, like here's a T, here's a T, here's a T, here's a T, and when they go to push a 5th element, we expand our allocation, so it's, you know, can hold 8 T's instead. 1, 2, 3, 4, 5, 6, 7, 8. And just sort of manage a pointer to this, right? Manage some sort of address of this overall allocation, right? An address of where we're storing our T's far away, and just mess around with that allocation as required. And then we could probably use a couple other fields to keep track of what sort of the current state of the Vec is in terms of like how many things we have and what our allocation looks like and so on and so forth. So does anyone want to suggest, I'm not sure how many chatters we have today, but does anyone want to suggest, I'm going to say we probably need 2 more fields. If this first field is some kind of pointer out to where we want to store the T's, there's 2 more fields that would be particularly useful to us of some, you know, name, some type. Does anyone suggest a field that might be helpful if we're trying to implement a Vec ourselves? So Mitch and Alex say len and size, which I think are really the same thing in this case. Len, size, both fine. I'll go with size, I guess. So size, and that's going to be of type probably usize here, which is just how many elements are currently like stored in the Vec, right? Like the user calls push once, there's 1 element in the Vec. The user calls push twice, there's 2 elements in the Vec. But we also need to keep track of, you know, if we've only sort of allocated room for 4 right now, and a user wants to push a 5th on the end, we need to expand how much room we have. So, as Simon mentions, it's probably worthwhile to keep track of a total capacity as well, which is how many elements are we potentially able to store right now with like this pointer here, right? Maybe I'll just call this like pointer or something. Inside this like allocation that the pointer is pointing to, how many things could we possibly store until we need to grow the allocation? So how many elements has the user actually put in the thing? How many can we possibly store at this point? So that all seems pretty good. Let's throw in the size. Size is a usize and capacity is a usize. Now, what type are we going to use for this, right? It's a pointer. And I've mentioned in the lectures before, pointers are kind of like references in Rust. So is this going to be like a reference to a T? But they might want to modify it or something. So maybe we need a mutable reference to a T. But then we're going to need a lifetime in here because it's in a struct. And, oh, you know, this is all getting a little complicated. Maybe we could do like a box of a T. That could maybe work. But then a box of T only lets us store 1 T. Sort of similar to the rest of these. You know, this is all a little too restrictive. And as Alex mentions, what we probably want instead is just a raw pointer, right? So a star something of a T. There's generally 2 options here, a star const T or a star mute T. And these are just like, it's an address, it's some kind of pointer to some location in the memory, and there's very little semantics past that. That's a rather untrue statement that I've just made there. There's rather little semantics past that. In fact, Rust still requires that you're following a lot of, you know, very particular rules, as we've come to learn throughout this course, and those rules, all those rules do still apply in the context of working with raw pointers, but they sort of let us opt out of all the static information in a certain sense, right? Like lifetimes or, you know, boxes model of things and so on and so forth. So really just like a raw pointer. Now, what's the difference then between star const and star mute? I'm sure, like, okay, so let's just choose one of them, star const, star mute. I guess we'll just do the first one, star const T, and it seems to compile, right? It's just a pointer to, in fact, this could really be a pointer to anything, because again, the pointer doesn't really carry many semantics, but we're sort of signaling to Rust that this is going to point to maybe a t, most likely. We're going to be looking at t's at least from this pointer. But so what's the difference then between a star const t and a star mute t? Well, let's say I had a t here. I can easily create a star const t just by saying let's say let my pointer equals, grab a reference to that value, and then turn that into a star const t like this. And that's fine. Now, you might go, oh, let's say you want to make a star mute t, you probably have to do like a ref mute value or something like that instead. And let's see if this works. Okay, fine. That's just a little thing. Right, and that seems to work as well. What might surprise people a little bit is that this, well, okay, fine. You're not surprised yet. Oh, okay, that doesn't seem to compile there. If I do this, it does compile. Right, that's what I was getting to. You might be surprised to see that this works. Take a borrow of value, turn it into a star const t, and then turn that into a star mute t with no unsafe or anything like that yet. Huh, that's interesting. So like, I suppose that means if I have this star const t, my pointer, then I should just be able to take that star const t that I had before and turn it into a star mute t. And yes, I can in safe Rust, mind you. So that doesn't feel very rusty. You know, I can just take a const pointer and turn it into a mute pointer straight away. Like, this is feeling a little suspicious. So let's go to the pointer primitive type here. So raw unsafe pointers, star const t and star mute t, blah 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 blah. I thought there was some. Where is the doc? There is some doc. Hello? Okay. There is some documentation on. Yes, I know. Provenance. Yes, provenance. Very cool. Where is the there is some documentation on the difference between star const and star mute. But I am missing it? Rust star const versus star mute. Where are these? Am I crazy? Maybe it's not in the standard docs. That seems weird. Anyway, so there's very sort of there's very specific differences between them that are like quite they don't really, how do I say this? There are some very like in the weeds differences between star const and star mute, but they are generally effectively the same. So one of the things they vary in is something called their variants, which is kind of funny. They vary in their variants, which I'm assuming Stack Overflow is probably going to talk about here. Do they talk about it? Yeah, the only other difference is the variance of the types, and I think that's all there is. Right. Oh, that's okay, fine. That's so basically like the only primary difference, apart from this variance idea, which we might not even have time to talk about today, is just sort of signaling their intent in a certain sense. When you write star const, you're sort of signaling that you're probably just going to be reading this thing. Maybe you don't even necessarily seem to own it. It's more of just a signaling, hey, this is roughly what I plan to do. But it doesn't really mean anything because you can always just turn it into a star mute at any time. So it's just more of a communication thing. And star mute kind of signals in like the opposite sort of sense. I maybe plan to mutate this thing. Maybe I actually plan to sort of own this thing and be responsible for it. But, you know, we're in raw pointer land, so we've thrown away all those nice safety guarantees. Well, we've thrown away some of the nice safety guarantees of Rust, and, you know, all the code that's being written here needs to be, like, pretty careful. And I still haven't used the pointer yet, so it's still okay without unsafe. Yeah, that's right. So if I tried to actually, like, use either of these pointers at any point, Rust would be very upset, because that's the part that's really unsafe. You can do all kinds of horrific crimes with pointers. It's only really like a serious problem once you get the thing at that pointer, essentially. And that's how Rust models this with unsafe. So, star const t, star mute t, what are we really plan to mean here? Probably star mute t signals a little better what we want. It does actually give us the incorrect variants. Again, something that we may or may not have time to really talk about, but that's something that can be patched up later with another type known as NonNull. So if we don't get time to talk about this, you can do your own reading if you're interested into things like NonNull and how that can sort of fix our variance problem here. Anyway, so a raw pointer to this allocation seems relatively sensible. Great. So what would we like to do next? Well, let's start off with new. So how are we going to make a new one of these? I guess we'll write self here. In fact, let's get Rust Analyzer to fill out these fields for us like that. Oh, why would you put them all on the same line, you horrible tool? Okay, there we go. That's much better. Okay, so when we create the Vec, one of these fields is really obvious. The size is 0, right? The user hasn't pushed any elements in, so the Vec should be empty. So that seems all right. What should we start the pointer and capacity off as? And here there's maybe not a necessarily correct answer. You could start it off with, say, like, let's say come up with some default number. Maybe that number to you is like 1. Maybe you go, oh, 1 is who's ever going to have a Vec with 1 element in it. Maybe we'll start it off with 4 elements, 8 elements, 16 elements, something like that. And that's certainly an option. The option that the Rust standard library takes is actually to start off with a capacity of 0. I think it's documented in new. The vector will not allocate until elements are pushed onto it. So the idea is maybe you have a whole bunch of empty vectors and you only push to them every now and like only some of the vectors get stuff pushed into them. You don't want to have a whole allocation for a whole bunch of vectors just to store 0 elements, just to store nothing. So instead we'd like to start the capacity off as 0, but if there's, you know, no current capacity, there's no allocation, what are we going to make this pointer? Maybe just we'll start it off as something like null. So I can do std pointer. There's 2 functions here. Null gives us a null pointer as a star const t. Null mute gives us a null pointer as a star mute t. So null mute makes our types check. And we have implemented MyVec new. So we can create a new vector. And so far this seems all right. So you're not really going to be able to do much with it yet. So I guess the next thing we'll think about is if we want to push into the vector. So we're immediately going to run into a problem, which is, so far for what we've written, if we push to the vector, it's always going to start with this, with no capacity. And so how are we going to like push to a null pointer, right? We need to have some sort of way to expand our capacity, right? So there's 2 cases where this happens. We might have no allocation yet at all, right? It's just being created new and there's no, there's no allocation like this yet. Or potentially we have allocated some amount of space, maybe 4, maybe 8, maybe 16 elements, something like that. And we've filled up what we've got and we need to make more room. In both of those cases, what's the relationship between size and capacity? Right? Like what's the like in the case where the vector has nothing yet and the case where the vector is now full, what's like unique to those situations in terms of a relation between the current size and the current capacity? Of our Vec. Size is equal to capacity. That's right. So we can say something here like if self size equals self capacity, then we need to expand. We need to expand, like we need to like, well, we need to like allocate more memory regardless. So that seems like a good idea. So this is our public interface here. We might need to write some more sort of private helper functions to help us do what we want to do, to make these public functions work. And so a function we might immediately start to think about is something like expand capacity. So maybe we say something like expand capacity will double the capacity of the MyVec if non-empty, or allocate room for let's maybe make some const default capacity, or like maybe that should be called something like first capacity. Oh man, I'm thinking better names. Initial capacity seems like the right one here. Initial capacity is going to be like 8. Maybe let's say you can, if you all want a different number, you can give me a different number. Maybe we'll do 4, so it's easier to test, I guess. Allocate room for initial capacity elements if there is currently no allocation. If allocation fails, this function will panic, let's say. Okay. So after, like, no matter what happens, after calling this function, you should have room for more elements. You should have room for at least one more element, I think is fair to say. Because if it's empty, then we'll have room for 4 elements. And if it's not empty and we call this, we'll double whatever we have. And say doubling a current capacity of 4 will give us room for 8. Doubling a current capacity of 8 will give us room for 16. So we'll always end up being like, if we just write, that is to say, if we just write self.expand capacity in here, then now we're always safe to push one more element, is what I'd like to say, essentially. So if the self size is equal to the self capacity, expand the capacity, that'll always give us at least one room, no matter what. And so then we're safe to push that element on. All right, so expand capacity. I mentioned before there's 2 cases here. There is the case where we haven't allocated at all yet. And there's the case where we have allocated, but we need to expand our allocation. Okay, so now we get into the fun stuff. And let me be completely transparent and say, like, I'm not coming into this lecture not having attempted to write my own Vec before. I have a bit of a crappy little implementation on the side, and I'm absolutely using it for like notes to refer to. If you see my eyes darting across my screens, I'm double checking what I'm doing because writing on safe code is tricky. I made a lot of mistakes along the way with that one. So like, I'm not to pretend I'm the big genius here. I'm consulting my notes along the way. So yeah, anyway, we'll get there. So, Rust has a allocation module in the standard library, which helps us just allocate raw memory. It's pretty handy. The functions that it has here that are of particular interest to us are alloc, realloc, and dealloc. So this is allocate me some memory. Reallocate is, here's an allocation that you gave me previously. I actually need a different size for that now. So usually this is like give me more memory, but it sometimes can also be I actually am using more than I need, so you can shrink this down now. But let's consider the case of I need more memory. What it'll do is it'll try and grow your allocation where it currently is. And if there's room to do that, it'll go, great, all done. You've got more room now. If there is not enough room to grow your allocation, it'll make a new one of the total size that you would like and copy all your old data into the new allocation. So it's a nice handy function for us. And then dealloc essentially lets us free the memory we're using when our Vec is eventually dropped. Right, dropping, that's probably something that we can think about as well. So something like impl drop for impl for any type t, drop for MyVec of t, and drop to do. Okay, so probably here we're going to want to like free our Vec and stuff like that. So we'll consider that a little later. All right, so in the case where we haven't made any allocations before, alloc is probably the function we're looking for. So it'll allocate us some memory. It wants to take memory through this struct layout, which essentially just lets us say, here's how much memory I'd like to allocate. In C, you might be used to alloc, like malloc, in C's case, just taking some amount of bytes. It's a pretty similar idea, but we just construct the bytes through this layout. You can just pass layout straight up like an amount of bytes, but you can use a little bit of extra convenience with it. So I'm going to make a new layout, and there is a layout array function, which is pretty handy. So it will basically tell the the allocator sorry, we just give it like how many elements of a certain type, let's say T, that we would like to include, that we'd like to allocate memory for, and it'll give us not only how many bytes that'll take up, but also the requirement on alignment is what we're talking about here, which is essentially some types require themselves to start on a multiple of n bytes essentially. So some types don't care at all. Place me at any address and I'll be happy, but a lot of types need to be stored at an address, say, divisible by 4, or an address, say, divisible by 8, or divisible by 2. Stuff like that. So this will end up handling all of that for us, which is pretty nice. We tell it we'd like to lay out an array of how many T's are the initial capacity. T's. Cannot find initial capacity. Are you crazy? Oh, did I spell it wrong or something? Initial capacity. What? Self::: initial capacity. I didn't know that the const scoping was weird like that. That's interesting. Cool. So lay out that many things. It also returns a result. Why will it return a result? Because if there's some sort of arithmetic overflow, if the total size would exceed the max of an I size, these are the kinds of things we're really not going to care about in this like demo, and we're just going to say unwrap a lot of these things and go screw it, it'll be fine hopefully. So now we have a layout, and we can say so std alloc, call that alloc function, pass it this layout, and hopefully that gives us back some kind of pointer. And it's going to probably be really upset because this is unsafe. So we're going to throw this in an unsafe block, and our safety is, well, what are the requirements on alloc? Safety, C global alloc. Safety, it's unsafe because you need to make sure the layout has non-zero size. And so that seems fine. Safety layout has non-zero size. So this is why this operation here is actually safe to do. So that seems fine. And finally, we now have a pointer to an allocation with that much capacity, so we can set ourselves accordingly. Self.pointer is going to be this pointer. Self.capacity is that initial capacity, like this. Cool. Now it sees that this is actually, like, alloc gave us a pointer back to U8s. We're expecting a pointer back to a T. This all doesn't really matter to us. Like, we can cast between pointer types as we like, and we know it should be fine to hold T's there. So you can just say, well, I could write the full thing here, pointer as *mut T, but the compiler is smart enough to see what I want to convert it to, so I can just say cast it, you know what I want to cast it to. And so I just throw an underscore here and it infers what I want. Cool. That seems pretty good. So now we should have a default capacity, and in fact, I think we're okay to start testing for up to like 4 elements. We can maybe leave this other case for later. Actually, we'll just do it now. We're already at like alloc and stuff like that. So if we already have an allocation, then we'd probably like to just double the current capacity, right? Reallocate what we have with double the room. And so we'd like to do something like self capacity times 2. This can like technically overflow if it gets so huge it's like it can't fit anymore, blah blah blah. We might as well just do a checked multiplication of 2, and if that happens to overflow, right, checked mul gives us back an option. If it doesn't overflow, then it gives us some of the result. If it does overflow, it'll give us none, and we'll just say, you know, if it goes wrong, then capacity overflow. And we'll say let new capacity equals this. Okay. So then we would like to call that realloc function. We've got a current allocation because we're in this else block, but we need to double the size of it and keep the old memory that's already there. So we want to use realloc, shrink or grow a block of memory to the given new size. It wants the pointer to the allocation. Great, we can get that. That's fine. It wants a layout and it wants a new size. So what is this layout for? It says the block is described by the given pointer and layout. Right. So what it's telling us is that the layout must be the same layout that was used to allocate the original block of memory. So that's basically, it's wanting like whatever layout we made for the previous thing. So maybe it's a good time to make a bit of a helper function down here. So something like layout for that just takes like n elements is some usize, and it gives back a layout. And we're going to take all this stuff here like that. So this is layout for self initial capacity. This here is going to be the layout an array of n elements. And now that we're going to use this should be self layout for. Now that we're going to be using the same layout for function everywhere, we can probably say something like let old layout equals the layout for the current capacity. So that should be like what was used, you know, the layout that was used when we wanted to allocate previously. So that's the old layout. We've got the new capacity that we want. So the new capacity, I'm going to have to turn that into a new set of sort of size in bytes. So we'll just make a new layout. Is going to be again layout for the new capacity. So actually maybe we'll do it like this. So here's what we want the new capacity to be. The old layout looked like this. The new layout should look like this. Now hopefully we're ready to do a reallocation. So it wants to know what's the pointer to the allocation that we're reallocating. That would be self.pointer, which we know is a star mute t. It wants a star mute u8. So we'll just cast that away. That seems fine. We'll give it the old layout. That's what it was allocated with. And the new size in bytes that we want, well, layouts, we can just look at the new layout that we want and grab that size in bytes. And that should be pretty happy. So new pointer is going to be call this unsafe operation like this. And it seems relatively happy with that. So let's check the safety. So we have another unsafe block. So we want to argue our safety. The pointer must be currently allocated via this allocator. We allocated self.pointer ourself. The layout must be the same as the one that was used to allocate that block of memory with a layout equal to old layout. Okay, self.pointer. Oops. New size must be greater than 0. The new layout is greater than 0 bytes in size, for sure. And the new size, when rounded up to the nearest multiple of layout align, must not overflow. We'll just say, and we assume it doesn't overflow. And I'm going to add like a cheeky emote here, just because like this is not a safe assumption to make. If someone makes a really big vec, then they definitely will run into undefined behavior. So this is definitely an unsoundness warning right here. But this is like sufficiently annoying to check for that we're just going to leave that in here for this lecture. But this is what I mean, where it's going to be like sometimes sound or like mostly sound, but there's definitely going to be some holes in what we write. And that's why we use, you know, the libraries that other people make when we can, because you know, because it's not entirely trivial naturally. But great, now we've got a new pointer. And so same thing, self pointer is the new pointer. Cast that as what we want. Self.capacity equals the new capacity. Awesome. Okay, so now we have a way to expand the capacity and generate like the current layout for n elements. Awesome. So this expands the capacity. We're always now safe to push one more element. So any questions about the, you know, the crimes we've committed in this expand capacity function before we go back and keep working on push? I'm going to double check my notes in the meantime as well. I mean, if I'm honest, that's like probably the hardest code right there. I mean, there's some gnarly stuff and we can sort of tune how far we go with this, but that's like the sort of most difficult part in doing like the actual allocations themselves. So I'm super happy to take a pause for any questions, or whether you feel like it's, you know, related or not. I'm super happy to field questions. Shouldn't we just add the initial size again rather than doubling every time? That's a really great question. So the reason I've sort of opted to double here is that's what the standard libraries vector opts to do. I'm guessing, is there here we go, capacity and reallocation. So blah blah blah. Automatically increased, for example, blah 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 blah. Double. No, okay, they don't really specify it. I know they do this, but maybe they don't talk about it here because they don't want people relying on it probably. But they choose to double as opposed to just add, say, another 4 elements or add another n elements, because it tends to scale better. So allocation, and you know, especially this reallocation in this case, can be really expensive in terms of performance. And so you want to allocate as infrequently as possible generally, but you also need to balance that with not using more memory than you necessarily need. So in our case, like, we could really minimize allocations by just going allocate memory for 1,000,000 elements straight away. And that'd be great. We'd probably only need one allocation like all the time, but we'd also like waste so much memory, because even if the Vec only uses 3 elements, we're paying for 1,000,000 elements worth of memory. So that sort of balancing act, not allocating too frequently but not wasting too much memory, the multiplying by 2 strategy is relatively good. So if it's getting bigger, we'll likely get much bigger. Yeah, that's the big idea here, is that if a user has 1,000 elements in their Vec, is that like, is the difference between having 0 elements and let's say is the likelihood from a Vec having 0 elements to 10,000 elements the same as the difference in likelihood between a Vec having 10,000 and 20,000 elements, essentially? Which is probably not true. Like, some Vecs generally will stay relatively small. Some Vecs might end up with an absurd amount of things in them. And so we try and balance for the things that are going to remain quite small and the things that have an absurd amount of stuff in them. But it's, again, this is not necessarily like the right way to do it. It's just like an option. Okay. And I guess and I can sort of argue if we were adding 4 each time, another way to think about it is the difference between going from 0 elements to 4 elements, or say 4 elements to like 8 elements. Is that roughly the same sort of, you know, does that feel the same as going from 1,000,000 elements to 1,000,004 elements? So that's sort of maybe a way to think about it. But again, not really necessarily a right answer anywhere. Okay, so here's our expand capacity. Now we're ready to write push. We know after this comment, we are, like, if we go to this, like, if we follow this pointer here and move like size t's across, there will always be room to insert a new t at the very end there. So we should be happy there. Now in my implementation, I wrote another helper function, which might be a good idea, which is function pointer to elem. So it takes a borrow of self, and a index, and produces a pointer to a t. So essentially, using this pointer that we've got in here, I would like to create a pointer to a specific index. So when that index is 0, it's probably just going to be the pointer itself. But if the index is 1, 2, 3, 4, 5, it's probably like past that's the start of that pointer. And this seems relatively simple. It's grab that pointer and we want to add on some amount, this like count here, units of t. So a count of 3 represents a pointer offset of 3 times size of t bytes. So essentially we're saying, you know, add on to this pointer index times, like index t's across, which is pretty nice. Note that this is unsafe though, right? Self pointer add is unsafe. That's a little interesting. Why is self pointer add unsafe? Pointer add. here. So unsafe, as we see, what's the safety here? If any of the following conditions are violated, the result is undefined behavior. Both the starting and resulting pointer must be either inbounds or 1 byte past the end of the same allocated object. So the pointer sort of needs to remain within like its logical boundary per like the allocation it's probably pointing to. It can't overflow, we've seen that, and it can't wrap around. So this is all about overflowing. So overflowing you don't care about, but this is interesting. The pointer needs to remain within or 1 byte past like the sort of relevant allocation it's pointing to. I thought that we could make pointers wherever we wanted and it's fine, but it's just when we use it that it's unsafe. Like this doesn't seem to sort of add up. And this is actually, this is all still true. And there is an explanation here, which is, consider, right, this one here. So the only advantage of this method is that it enables more aggressive compiler optimizations. So this is interesting. There is another function, wrapping add, which does the same thing, but is not unsafe at all. Right, this operation is always safe, but using the resulting pointer may not always be safe. Compared to add, which is the one we were just looking at, this method basically delays the requirement of staying within the object. Add is immediate undefined behavior when crossing object boundaries. Wrapping add produces a pointer, but still leads to undefined behavior if it's dereferenced, if it's out of bounds. Add can be optimized better and thus is preferable in performance-sensitive code. So it's really up to you which one you use. They're basically saying, like, there's still going to be undefined behavior if you screw up either like now or later, and we probably plan to dereference whatever pointer we get out from this. So it's just up to you like where the unsafety occurs. I think we're fine to say that this is, we'll just like use add here and throw an unsafe block in. And the compiler seems happy with this, but we still need a safety comment. And this safety comment is maybe a little tricky to argue. If we go back up to here, we need to make sure that the starting and resulting pointer must be inbounds or 1 byte past the end. But a user could give us an index that's like completely ridiculous. Right? They could give us an index that's just not valid at all. So we have two options. We could say if the index that they give us is greater than or equal to our current capacity, then like do something here, like, you know, refuse to call self pointer add, and that maybe sort of prevents undefined behavior. So yeah, that's exactly what we're saying there, a guard clause like this, and just throw some sort of error. What's another option that we have here? If we don't want to have any guard clause but like we don't want to like violate, you know, we don't want to write really bad Rust that makes everyone angry, there's actually one other option that we can do with this function here and not have to worry so much about this unsafe. Does anyone have an idea? Sorry, I accidentally swallowed some ice. Is anyone? Maybe someone's typing something out, but what I was looking for is we could also declare this function to be unsafe as well. And like note some sort of safety guarantee, like safety requirement that says index must be a valid index within our current pointer kind of thing, something like that, which essentially says we're not going to check it, so you better make sure that it's actually okay. And then that saves us on a bit of code that needs to check it every time at the cost of, you know, more people having to be careful with using this unsafe. I think just to demonstrate the idea of having an unsafe function here, I'm fine to keep it like this. But they're both options are perfectly valid. Okay, so now we have a function to get us a pointer to some element. And so in push, we should be able to write something like self dot pointer to element. So let some pointer be self dot pointer to element, and we currently have self dot size elements. So the index to like the element that we're interested in is actually just self dot size. If the user currently has 3 elements in their array, indexes 0, 1, and 2, we're going to insert into index 3, which is just the size itself. So this will give us a pointer to that. It's unsafe. So we have to put an unsafe block, and we're going to write safety. We just expanded the capacity if required, and so self.size will always be a valid index, something like that. And again, this is the process of us essentially checking on behalf of the compiler where it isn't able to check these things. So we do that. Now we have a pointer, and finally we should be safe to store that user's value at this pointer. This pointer should be the location of some of that t. So we should be able to say something like, well, I'll forget the unsafe for a second. At this pointer, store their value. Now it's going to say this is unsafe. So we're going to say unsafe here. And our safety argument is something like the pointer returned by self.pointer to elem is a valid pointer within our Vec allocation. So, oh no, this is not safe. This is actually not safe. This is kind of cool. In fact, did I get this right in this one? Okay, I did get it right in the other one. This is actually not safe. Oh, this is a really tricky reason. So, there's always a valid pointer within our Vec allocation. So we're safe to write to this value. Write to this address, rather. This is a really sneaky source of undefined behavior for us. Unsafety is infective. Yes, we're going to talk about that as well towards the end of this. This is a really dangerous line of code right here, which is, again, this is part of why writing unsafe Rust is really particularly tricky. Does anyone, maybe this is a good thing to break over for the next few minutes you can think about. Why is this line of code unsafe? So I'll point out like what you can assume for sure. The pointer is genuinely a valid address to a valid location that we can write bytes to. The value that they've given us, this t, is a valid t that's, fine to be written there. One thing I will say is that the stuff at this pointer, value can have any size. Well, value is given, it is still a t, so t's can't vary in size. If they could vary in size, this is actually an interesting thing in Rust. Anytime you have a generic bound like t, it by default implies this. It requires that t has a known size. You actually need to specifically opt out of that, saying that the t is optionally not sized, doesn't have a stable size, which things like box actually do. So if we look at a type like box, we'll see that t is allowed to not be sized, which is kind of interesting, but we haven't said we're not allowing unsized types here. So t will have a known fixed size, and all the sizing should be correct. So I'm giving you this for free here. Pointer is a valid pointer, an address within our allocation. That's fine. Value is a t. That's correct. The location that we're trying to place it is also correct. Alignment we're not going to worry about today. So that's all fine. It's also fine to write to this place. But the thing to think about, the context to think about this in, is that currently at this address, there may be uninitialized data, right? Like when we say allocate, when we say alloc or realloc, the memory it gives us will be uninitialized. We don't know what that memory will be. And there is something really sneaky in this line here that will actually try and read that uninitialized memory. When we say at this location, store this value, for some reason, and this is what I'm asking in the chat, try and think of what this reason is over the break. For some reason, this like star pointer equals value will end up reading the value at the pointer. It'll end up reading the value at the pointer before the value gets written in for a certain purpose. What is that purpose? Why does it try and read what's there first? And I'll also, one more thing I'll give you is that it's not just like some silly syntax thing. It's not like, oh, if you wrote it slightly differently, like this star pointer reads it or something. No, like this genuinely is a valid line of Rust that says write value into this address here. There is genuinely a very fair reason that Rust does read the value that's there at this address before inserting this. Have a think about that. See if you can come up with any ideas. I'll see you all at, let's call it 9:08. All right, so see you after the break. All right, so we're back from our break, and I seem to have stumped the class, but that's okay because it is a really gnarly thing. The trick here, unless if anyone wants to take a last stab, as we're coming back from the break. In fact, I can even write a little example while if anyone has any last ideas, what it might be. Okay, so I don't see any other ideas, so I'll explain it now. When this function foo is called, it creates two allocations, box new 42, box new 123, like this. When foo finishes, when foo, the function's, scope ends, these two values will be dropped, right? Drop here being the trait that we've talked about a few times, which is custom code within a destructor. When a value is no longer needed, Rust will drop that value, e.g. when it goes out of scope, and drop lets you run some code when that value is about to be, when it's about to be, I don't want to say dropped, I guess when it is about to be dropped in a certain sense. So for a box, that's really important, because what does a box want to do what does a box want to do when it's dropped, right? So let's say a box has some value t, and when that box gets dropped, it wants to free its allocation, right? It did malloc when you said box new, malloc me room for 123, malloc me room for 42. When that box gets dropped, Rust wants to free it so you don't get memory leaks. Now, if I write the code here, a equals b, set a to be equal to b, two things have happened here. One is that we've taken this b and put it into a, but in doing that, we've overwritten a. Right? Do we see that? In that, like, this box new 42 doesn't really exist anymore. It was in a, but then we overwrote a with b. So, like, the two things will happen in this line. Sure, yeah, it's going to set a to be, the contents of whatever b is, but it also needs to make sure we don't end up with a memory leak here, in that a's value doesn't exist anymore. So when, the drop code runs down here, like, a literally, like, this box new 42 doesn't exist anymore. And so we can't, like, forget to drop it. So right before it says a equals b, it will drop the original value of a. So you can imagine this turns into what is effectively drop a equals b, like that. That's essentially what it does. And I assume this, typically, where is it? It said, the most common way is when it goes out of scope, but it doesn't really, maybe it doesn't say otherwise. Okay, whatever, that's fine. But writing like this a equals b will implicitly drop a in case, there's some important code that needs to run there. Like it's, freed, or it needs to get freed or something like that. So then the problem with this is that if T has some custom drop implementation, like say if T is a box of something and it needs to be freed, then dereferencing, saying set this T to be this new value, it'll go access this potentially uninitialized memory and try and drop that. And that's, immediate undefined behavior. So on assignment, the pointer attempts to free whatever was previously living at that address. Yeah, that's absolutely right. So that could be a little dangerous. And so Rust has thought about this, and they have a pointer write function here. Overwrites a memory location with a given value without reading or dropping the old value, which is pretty handy. So it doesn't drop the contents of that old destination. This is safe, but it could leak allocations or resources, so care should be taken not to overwrite an object that should be dropped. We're not going to care about this case, to be honest. It's safe to leak things. Like, leaking things is not unsafe in Rust, because it's not going to lead to undefined behavior. There was a huge fight in the Rust community a few years ago about whether, like, mem leak, there's a function literally called forget, stdmem forget, which essentially like leaks a value. This used to be unsafe because it was like, this is a stupid function and it's probably going to cause you headaches, but it doesn't cause it won't ever cause undefined behavior. And so there was a big fight for a while over whether that function should be unsafe or not, and eventually the Rust community decided, well, it won't cause undefined behavior, so therefore it should be safe. And they changed it from unsafe to safe before Rust 1.0 was birthed. Anyway, so we're going to use write instead, which is a little safer for us, a little more sound. Pointer.write, but naturally it's still definitely unsafe, and so we need to have this safety argument and this unsafe block. Great. That should genuinely be push done. Awesome. So pop and get are still to go. and then we'll test a whole bunch of it out. Okay, so to pop the last element off the vec, we should just be able to like decrease the size by 1, give them that value back. We also need to make sure the vec is not empty, or we could end up with some unsoundness. So if the current size is 0, right, if they have no elements in the vector, then pop shouldn't do anything and shouldn't give them anything back. However, if there is some elements in the vector, then we should be fine to do this. So we can say self.size, subtract 1 from that. So we're taking the last thing off the end, so the size will decrease by 1. Then we can grab a pointer, self.pointer to which element. Well, now that we've subtracted 1 from size, it should just be the self.sizeth element, essentially. Right, so if they had 3 elements in the vector, that would be index 0, 1, 2. We subtract 1 from the size, that gives us 2. The last index is 2, so that seems right. This pointer to element, as we've noted, is unsafe. So we'll want our safety argument. Safety, we checked that the vec is non-empty, and self.size now represents the last valid member of the vec due to the -=1 operation. So that seems fine. It's just getting upset about it not returning the type yet, so that's fine. So we've decreased the size by 1, so we should never end up like using that value again, so that's fine. We've got a pointer to it, so now we should just be able to read that pointer, which is very unsafe as well. So we'll say let the value equals read that pointer. Safety, I guess we can just say same as above. It's really like the same argument. This is a valid pointer t to read because it represents a valid member in the vec that should have been pushed on over here. So read it, and then finally we can give back some value like that. And that should be pop. Pretty happy. Cool. Finally, I guess we just have get to go here. Get. Nice. So just get me a single element. And this should honestly be pretty similar to pop. Like they're both in essence reading it, but like slightly different ways. This one takes an index, but they're both giving back an option of t. And also pop modifies the size as well, I suppose. So I guess we're going to go, there's still a case that's bad. In our case, it's if the index they provide us is greater than or equal to the number of elements they've got, then that's not a valid index to get something from. Otherwise, don't modify the size. We just want to get it. Pointer to element of index. So we just checked that the vec, or that the index provided points to a valid, or not points to, represents a valid element in the vec. So that's fine, and same as above, and that seems all good. Now we've got get. Cool. I guess we get rid of this function foo. Let's test it. Is there any errors? No, I don't think there's any errors. Oh, drop. I guess we haven't done drop yet, but we can do that a little later. So does this work? Cargo test. All nuns. None. Okay, that's not ideal. All nuns. Why have we got all nuns? So what's this doing? It's going vec.get and vec.pop. So it seems like these are always returning none. This is checking if self size is 0, and this is checking if index is greater than or equal to self size. Can anyone see the bug that we've forgotten here? Can anyone spot the bug? Why are we always getting back none from pop and from get? Something we've missed right around here. Size not incremented. That's right, yeah. So I've just forgotten to do self.size plus equals 1. Right? So you can imagine if it was forgetting this one, that could really be like, in our case, it's just the vec is not doing anything useful. It's not giving us the values. If I forget the self size minus equals 1 here, that could actually be a serious soundness issue. So this self-size minus equals 1 is really related to the validity of an unsafe operation that we're doing down here, which also ties into this idea that unsafe is a little infective, as Mitch mentioned earlier, in that this unsafe operation kind of makes what we're doing over here unsafe, in that it like really relies on it. And if you deleted this line of safe code, it's, you know, it's now unsafe. So unsafety really needs to be considered in the entire context that it's working in, which we're going to talk about again in a little bit. So hello world, this is COMP6991, and then the rest of the indexes were nothing. Then we got popping off 6991 is this, and then the vector just had hello world and a bunch of nuns left. So that looks great. It actually looks like it's working correctly. Now let's try and get a bit of an idea for undefined behavior. So let's run this, or let's test this under Miri. And Miri seems to say that it's okay, like it seems to be working. Like there was no undefined behavior along the way. So let's let this test case pass in this case. But Miri does notice an issue now. Now that I don't just like panic the function before it has a chance, Miri noticed that the memory gets leaked. So the following memory was leaked. Oh yes, we haven't done any like dropping in the Vec. So we probably need to consider that. Otherwise we're just going to leak all these allocations that we're making. So what can we do in here? Well, we know that we have our allocation here, this pointer, and I think we should hopefully recall a little earlier we saw that there was alloc, right, to allocate memory, realloc, and also dealloc, or like free, saying that we're now done with this allocation, and it just takes a pointer and a layout, and you know we've sort of done this little dance here before. So we'll say the layout used to allocate what we've currently got is going to be wasn't it layout for? Ah, that's interesting. So layout for, are we going to be able to access this? No, that should be fine. Why is this not saying it? Self layout for self.capacity. Is it just no method found for? Oh right, sorry, self : layout for. I'm being silly. This doesn't need to take self at all, and so we need to use the slightly different calling syntax. Sorry, I was confusing myself for a little bit. So get the layout that was used for whatever we've currently got, and then we can say alloc dealloc like this. We want to deallocate the pointer we've got with that layout, and this is unsafe. And our safety argument is that we allocated this pointer ourselves using the layout provided. Whatever, a bit of a weak argument, but it's probably good enough. And we just need to cast this pointer so it's happy. Okay, so that should deallocate the memory that we stored for the vector. So let's see if that fixes Mary's memory leaks. It does fix Mary's memory leaks, but it probably shouldn't. I'm surprised. Like, that should fix one of the memory leaks. For sure. Oh, because these aren't. Okay, great. So that fixed our memory leaks. Great. Okay, awesome. But we still have potential for memory leaks. Does anyone have an idea where memory leaks could still potentially appear? Does anyone have any idea where memory leaks could still potentially appear? There's something that this drop here is actually potentially missing. If it's a vec of pointers, yeah, if it's a vec of things that might need to be dropped. So what if these here were all actually like strings? Like not strs, but like actually own strings that allocate their memory, right? If we test this again now, Mary's pissed off that, okay, was dereferenced after this allocation got freed. This looks to me like, that's 147. It's saying that this got freed. Why does it think that that got freed? Oh. Do we have some UB? Ah. Right. It looks like, yes, when we pushed it here, it's still, we're like writing this value. Like if I go to stood pointer right, it takes, well, no, this one takes a source T. It does not drop source. Why is source getting dropped? Let me see. Does dot right do the same? Yeah, without reading, oh no, that's the old value. Let me just, so this is what I think is the potentially the correct thing to do here. No, but this was moved away. So why, that's a little strange. Why does it think this has already been freed? Push, huh. Okay, that's a little weird. Maybe we'll save that for a little later on, but the idea here that I wanted to look at was before we actually like actually free the container that holds all these elements, we want to drop the elements themselves in case they need to like do something. So I could say for index in 0 to self size, call like drop, right? And the trick here is to stood pointer drop in place is essentially like drop me a value that I get from a raw pointer. Something like this, essentially. This is unsafe. Yes. Like that. And you're upset because for index, is that actual underscore? Yeah, that was an actual. Nope. What are you upset about? I'm going crazy today. 0 expected. Oh, missing the in. Oh, for index 4. Okay, great. For index in. There we go. That's it. Then basically just drop the like the each element in the thing. This is not going to make Miri happy because it's already pissed off before we get to that point. But this seems really rather strange to me that it's this is the kind of this undefined behavior I was not particularly expecting to show up in this lecture here. Is there anything weird with pop? Read the value and then give it back. That's really strange. It does not drop source. Okay. Well, I think we're going to say that is a fun bit of undefined behavior that I'm going to have to look a little closer at after the lecture because we still have other stuff to talk about, sadly. But like, look, it still works, right? As long as it doesn't have types that, you know, might be reliant on not being dropped or something like that. Anyway, that was the last sort of important thing. There are more things that you can play around with. Like I said, changing this to a non-null T is an interesting idea. Changing this to be a no dangle T with the drop check eye patch. There's all kinds of sort of improvements that you could make that goes a little past what we're probably interested in 6991. And there's still a little bit of unsoundness hanging out in here that I will have a bit of, that I'm going to have a fun time poking around at and then amending in something. I guess we don't have a good place for amending in lectures, but I guess probably updating the Git page for this and also maybe like an announcement or something like that, or an email. I don't know. I'll figure it out. But I'll have to figure this out in my own time. That's where I'm happy to leave our insane unsafe for now, because we have some insane FFI to do as well before the end of the lecture. So do we have any questions for like what we've got so far? Oh no, there's one more thing that I really wanted to talk about, which is this is actually really dangerous as is written right now, because we could write some unsafe code, some safe code that just like seriously breaks like our current program. So for example, if I had a function foo that's like create a new MyVec, let v equals MyVec of new, and let's say, okay, v dot push 42, something like that. Let mute v, like that. So this is all fine. Technically, this code right here could write something like v dot size equals 1000, and also v dot capacity equals 100,000, right? Like this code, this safe Rust code could write this, and that would be really rather bad. And this is another idea of this unsafety is infective, in that MyVec has a data invariant that this pointer must point to, well, either as null with a size of 0 and a capacity of 0, or it points to an allocation that has room for capacity t's and has currently, size valid t's stored there. But if another, function can come along in safe Rust and just destroy those things, it can cause some horrible unsoundness just by saying like, v dot pop here. This would lead to undefined behavior. And so generally what we like to do is whenever we have some kind of unsafe abstraction, wrap it in its own kind of module. So I might make like a MyVec module that wraps around all this gnarly unsafe here, right? And then grab all this code that all gets indented across. And then we say, like, make very clear which parts are public. So in particular, these fields here are not public. They better not be public, because otherwise people could screw up our data invariant and our unsafe code would do horrible things. Okay, fine, we'll put that in here just to make you happy. And so now, if we go down to this foo code, which I seem to have stupidly deleted. Did I actually just delete that? Okay, well, fn foo, if we do let mute v equals MyVec of MyVec new and v dot push 42, if we say v dot size equals 1000 here, now it won't work because we don't have access to this private field, and therefore we can't change it. So that's actually okay now. So you could still get away with putting this foo function inside the module here, but at least it's not getting mixed with actual code that's meant to be like genuinely safe. It's pretty clear that this here is like, unsafe module over here, safe code could potentially break invariants, but we've sort of cordoned it off to the minimum viable section essentially. So yeah, it's very common to wrap your unsafe code, like your unsafe abstraction, in its own module, so it doesn't infect the rest of your module, the rest of your crate, whatever it is. So yeah, that was the last real important thing that I wanted to talk about there. Okay. So any questions you have about this, feel free to throw them in the chat, as long as the question is not, why is it unsound right now? Because I don't have the answer to that question right now live during the lecture. But otherwise, if you have a question, type it out and we'll jump across to it. But otherwise, let's just try and start to speed through a bit of FFI as well. So FFI is pretty cool. It essentially, well, let's just sort of talk about things generally. If I'm writing a Rust program and I want to talk to some external program, some other, code that might not have been written in Rust, how would I go about doing that? There's a few sort of like, here's some existing ways of potentially talking to between different programs. So you might want to spawn that other program. Let's say it's a Python program or a C program. You spawn that program as a child of like your program, and then communicate through, say, like standard input, standard output. If that program wants to talk to you, maybe you want to like be spawned by them and communicate in a similar way. There's other methods of communication as well. You might want to communicate across, say, a file system, right? So like I interact with this program not by like, running each other or calling functions on each other or stuff, but we just like read and write files that we both know about, or maybe we communicate over a socket, like, talking over a network, right? So it might be like send bytes over this port, 42, and I'll listen on that port and I'll talk to you on that port. You might go a little further and go like, oh, you know, dealing with these raw sockets and bits and bytes is so annoying. Let's use something like HTTP, which is essentially an abstraction on top of something like a raw socket. And go, you know, I'll send you a request that looks like this, and you send me a response that looks something like that. You know, many people will opt for something like this. You could go real crazy with it and send, you could tape a piece of paper to a pigeon's foot and fly the pigeon across to the other program. Maybe a little less effective, but there's oodles of options on how you might want to talk between, you know, different programs. But what about performance? You know, with all this stuff spawning, be spawned, file system socket, HTTP, carrier pigeon, they're probably going to be relatively slow, you know, compared to what we're going to look at in a second. And so, like, you know, in terms of how much memory it uses, or you know, how fast it is to communicate, you know, it might be a little too slow for you. It might not be available. Like, what about platform availability? Like, do all of these options work in, say, like a embedded or like niche, you know, small microchip? Spawning, yeah, probably not. File system, you might not have one of those. Sockets, networking, you might not have that either. Carrier pigeon, I doubt an Arduino is going to start learning how to talk pigeon. And so, you know, sometimes when you care about stuff like this, you might want to consider FFI, which is busting through the wall here. So FFI is really just a way to create a like program that has, you know, that allows different programming languages to talk to each other over a common interface. In this case, a foreign function interface is what it's called. So it's essentially allowing different languages to call each other's functions through a shared understanding, essentially, a shared understanding of how someone ought to call a function in a program, which is known as an ABI, an application binary interface. So C, you might look at C and go, C is a programming language. I know this. What's C? C is a programming language that lets me write code and I can compile it and run it. And yes, that's all true. But C is also these days very much like an ABI, in that it's a very common, like, lowest common denominator between a lot of languages, right? If I want Rust to talk to C++, or if I want Rust to talk to the operating system, or if I want, you know, C++ to talk to, I don't know, maybe like Zig or something, I'm not sure. Often people will just use C as like the common ground between everyone, and like make a function that looks like how C would do it, and then I'll be able to call it through that. And so we can compose together C code and Rust code and have them talk to each other across this FFI boundary, right? So like the Rust code has, you know, the strict Rust parts, the C code has the strict C parts, and then they expose like an interface in order to be able to talk to each other. And yeah, that interface is what we generally call the foreign function interface, and it lets you call functions between the two. And we're going to go psycho mode with writing some FFI code as well, because that's really fun. So some useful resources when you're looking at FFI, the Rustonomicon, which was that Unsafe Dark Arts book that we looked at the other day, has a section on FFI that starts off all right, pretty easy, and then gets gnarly at some point. There's the Rust standard library FFI module itself as well, which, you know, talks about things you might want to care about if you're learning about FFI. There's an unofficial FFI guide by Michael F. Bryan, which I think some people tend to use, but is also somewhat incomplete, so your mileage may vary. And also the libc crate, which essentially FFI is the whole C standard library, right? FFI bindings to libc, the C standard library, is also a pretty interesting crate to look at when you're trying to talk with C as your common interface. So, has anyone heard of curl? Curl is an awesome program that I can put in like a URL like this, google.com, and it'll go and fetch that web page. So it's saying Google spits back some HTML that says, hey, this page actually, we don't use google.com here, we use www.google.com, and then you'll get the actual like page itself right? This is like the code that runs google.com. And there's all kinds of different, websites you can look at here. youtube.com. Yep, there it is. My personal website, insu.dev, just spits out hi there with a tiny little piece of secret HTML. Does anyone have any like particularly interesting websites that they want me to pull down with curl? It's a pretty good tool. It has an insane amount of like options in how you might want to fetch a web page. Mitch uses it all the time. And so yeah, curl's awesome. It's, very famous as probably one of the most important libraries of all time, one of the most important tools of all time, for, computing on Linux and stuff. And it will note here that it says curl is powered by libcurl, right? Libcurl. So I don't have a manual entry for libcurl, sadly, but I do have libcurl installed on my system. So I can do package config list all, and it says I have the curl library. So the way that curl operated is it created a C library, right? Like literally written in C. And let's look at an example here. Let's say if we're trying to get something over HTTPS. So it wrote a C library that you can, call their functions, curl blah, curl this, curl that, curl blah, and use that to get information from the internet or from whatever network you're going over. And then they wrote a command line tool called curl that uses the libcurl library in order to provide a convenient command line interface for people, working on Linux, systems administrators, users, developers, whatever. Now, this curl library is written in C, but what if we would like to use that in Rust instead? And the answer is we can. And I'm going to get really insane with it. And we're going to probably take some shortcuts that are not okay to take, and it's going to be fun. So I'm going to grab a few things. Only one of your exercises this week is talking to a function over FFI, and I think it's honestly pretty easy. But we're going to talk to curl over FFI, and it's going to be really hard, and it's going to be fun. So let's do cargo new. We did Vec insane, so this is going to be curl insane. Great. Now, let's look at the simple. This is curl's sort of simplest example for how to get a web page in C. And we would like to do this same thing, but from a Rust program by calling this C code directly. So there's a couple things I need. I definitely want to have this simple example just to show me what things I'm going to need to tell Rust about. I sort of need to tell Rust, here's the different functions and the types and stuff like that, and it will go look for that function and then link it for me, essentially. It'll go link, oh, when you call this Rust function, it's actually not going to be the Rust function at all. It's actually going to go off and call this C function instead. And I can start us off by doing that. I can start us off doing that by defining an extern block. So I write extern to say, I'm going to define some functions in here, right? I'm going to define some functions, but I'm saying they're coming from somewhere else. And I need to tell it what sort of ABI, what you can imagine the language of calling functions and stuff, what it pertains to. In this case, it's C, and it's honestly usually C. Most of the time you see an extern block, it's going to be C. And then in here, I just define the functions and their signatures and stuff that I would, like to be able to call. And using unsafe, I'm able to call these functions from C. So in particular, it seems like we need this curl easy init function, curl set option to tell the URL I want, and curl easy perform to actually perform the request. Maybe we'll look at cleaning up if we can be bothered to / have time, but cleaning up, it says always clean up. We're going insane with it, so we can maybe be a little crazy and not clean up. Okay, so let's start copying these function definitions in. So we need to write it as a Rust style. So the return type doesn't go here, it goes over there. Oops, that's not what I wanted. I wanted that. And also we don't write curl pointer like this. We would say something like a raw pointer to a curl. And so that's fine, but Rust doesn't know what curl is. So I might go hunting in the header file. So C programs often come bundled with a header file, which tells you like, here's all the functions and types you have available to you. And a header file can be really handy when generating these extern blocks over here. So I need to tell it to call this function. This function is going to return a star const curl. What is a curl? And I would go looking through this, this header file, looking for curl here. I believe we have typedef void curl. So when they give us a pointer to a curl, that's just a void pointer from C, which basically just means we don't know what this pointer points to, but it's just going to be an address. And fortunately, Rust has types to help us out with this. From this std FFI module, we can get things like C void. So we know, maybe it might make a little more sense to write something like type curl equals C void. Right. I got this from here. Curl is a C void value. And so therefore, when they return us a pointer, maybe this is more like a star mute, I guess. It doesn't really matter. That's going to be a star mute curl like this, which is just a C void pointer. So Rust is already happy. It goes, right, okay, cool. So there's going to be a function that looks like that. I trust you. All right. So that should let us initialize our curl. We then need this set opt function. Okay, so let's take the definition here and reorder it to look a little more like Rust. Curl star handle. This really should be written as handle is not a star curl, but a star mute curl like this. Curl option is the same as saying option is a curl option. And parameter here, what the heck? Parameter doesn't even have a type. Well, that's annoying. What is parameter? The parameter can be a long, a function pointer, an object pointer, or a curl off t. This is our first step of we're going to go a little psycho with it and go like, okay, it's saying that it'll be happy to take anything of any of these types. Do we really need all these types? Like, let's look at this example. Curl opt URL. So that's a pointer, like a string here being a char pointer. So that's going to be some kind of object pointer type. This here is a long follow location. If it's redirected, follow the redirection. Let's just say we don't care about that, to be honest. And like just assume it'll be fine. So let's just say I bet it'll just be like some sort of a pointer, and we'll just say it's like a C void pointer. It'll figure it out if it's close enough. In this case, we can go a little psycho with it. It still doesn't know what a curl option is or a curl code is, so we are still going to have to consider that. So curl option, what does that get used as? We have curl opt URL, curl opt follow location. Let's look in the header file. So what was this? Curl option. Okay, so they say that curl option, that's this thing here. No boy, that's long. It looks like there's lots of curl options. Is a enum. Curl option is an enum, and it looks like of a whole bunch of things. What's this curl opt? It's a macro that says, takes an NA, a T, and an NU, and it says NA equals T plus NU. Okay, so what it's essentially saying is that for each of these things that it writes here, it'll say something like curl opt write data equals curl opt type CB point plus 1, or curl opt string point plus 2. So it's essentially defining a whole bunch of constants with these names on the left equal to this number plus this number. And like, okay, so in Rust, we could write something like enum curl option. And like, do we really need to keep all of these? Like, probably not. We can just go a little psycho with it and go like, this is really the only one we need here to specify the URL. So we go, oh, there's curl opt URL. So curl opt URL is going to be equal to curl opt type string point. String point is an object pointer. Object pointer is this number here, 10,000 plus 2. 10,000 plus 2. So this is just going to be 10,002. Right. And like we could put a whole bunch of more options here if we needed them, but I think we only need the URL just to sort of do our proof of concept. And this should have the same layout. It's just going to be a number, right? And this is just expecting these curl options are also just expecting a number of, you know, one of those numbers there. So we've got our curl option, and then we need to consider what is a curl code. Curl code. Here, there it is. So this is actually just an enum of all these values. And actually, there's no real macro magic going on here. So it's, again, just another enum. But since this looks like syntax that Rust should be relatively happy with, I'm happy to just like grab this one and go enum curl code is going to be this. That seems reasonable. It's complaining about the camel case stuff. So we'll just go like allow non camel case. What's the non-camel case types? I think, yeah, that gets rid of all these warnings. Unused, whatever, we'll forget about it. Just throw in like a stop warning me about every little thing, Rust, please. Cool, and now we have an enum that should be compatible with this. Okay, now interestingly, Rust doesn't guarantee exactly how it's going to make these, you know, these types that we've defined here look, because it wants to be able to reorganize the types in future if it needs to in order to like optimize and make things work better. So we actually need to explicitly tell Rust, I would like you to lay out this type the same way that a C compiler would, and we can say that by writing Repr C. So essentially lay this type out like if a C compiler wrote it, which is exactly what we're looking for, given that this was like fed into a C compiler here, and we're trying to make our Rust code look roughly the same. Okay, cool. So that seems to work. Set opt. What else have we got here? Curl easy perform. So we can look at that one, or in fact, we can, like, just to be clear, we can also look at these. Oh, okay. Apparently not. Curl easy perform doesn't seem to appear in this header file. It probably comes in from another one, which is annoying, but we'll just grab it from the docs instead. So fn curl easy perform, lay this out like Rust would, curl star, that's going to be this is a blah, that's this. All right, something like that. And actually, we've already got all the types already set up for us, so that seems all happy. Awesome. I guess how bad's the cleanup type? Cleanup, I think this should be fine. So fn, this returns void, which in Rust we just like specify as not returning anything. You know, void in C just meaning I don't return anything here. And this just does our cleanup there. Cool. So now we've specified that all these functions are going to come from somewhere, but generally in Rust we need to tell it where these functions are going to be pulled from, because it's not just going to like look across my whole system for like where it might find any of these functions. So we can specify that with a link at the top of this extern here, where we say look for a library called libcurl. Note that you don't put the lib there. If you wrote lib, it would actually look for libcurl essentially. But you leave off the lib and we write, hey, this is meant to come from curl. It'll search on the system for libcurl and hopefully find these functions from there. If it can't find these function definitions or they don't seem to line up from what it's seeing, we'll get an error out of like Rust C or the linker where it says, hey, these linkages don't really line up. So we're hoping that, in fact, we can even just test this now by saying cargo build, and it seems to build, meaning it probably finds curl and finds these functions. If I wrote like curl like typoed it, you'd see this huge linking error saying, hey, I don't know what L-curl is. So you are still like somewhat, you know, safe from writing these little mistakes like this. So let's grab that example and see if we can run it from Rust. So first they say run curl easy init. So let curl equals curl easy init, right? And calling another function over FFI is definitely unsafe. Why is it unsafe? It's unsafe because it's not calling like a separate program doing a separate thing. These are now, like if we look at the slide again, these are now like in the same program. So as soon as you're calling out to something like C or C++ or any other language, as far as Rust is concerned, all bets are off. That's really dangerous because it could screw with all our memory. We're living in the same program now. So this is always like calling over FFI is just always inherently unsafe. And just to save having to reason about every single unsafe, I'm just going to do a huge unsafe block and you know, go a little insane with it and be like, yeah, it'll be fine, sorry. So next we want to tell it the website we'd like to get. And I love that this just like this, I paste the C code in there and it just like works. Let's grab my website. Oh no, it didn't quite work, sadly. Curl opt URL, that's probably going to be curl opt URL, because we're in Rust. Curl option, what do they call it? Curl option. There we go. Curl option, curl opt URL. There it is. And also, this here expects to like some sort of pointer, but we've got some ref tick static stir here. We need to create a string compatible with how C views strings. Unfortunately, there is this C string type from FFI. Right, std FFI. This is specifically a module to help us help with interoperability between this and languages like C. So let's say create me a C string, which is my website. It's only valid if the C string doesn't contain any null bytes, because C uses a null terminator to denote the end of the string. So that's why it returns a result, and I'll go, it's fine, just unwrap it. And pass it in the string as a C stir, as a pointer, as whatever kind of pointer you want it to be. Again, going a little psycho with it. So we've got a C string here, which is like it's analogous to like a string, which is sort of heap allocated and stuff like that. We want to turn that into a C stir, right? As C stir, which is analogous to the stir type in Rust, which is just forget having a size and a capacity and that sort of stuff. Just be like a pointer to a string, and then get that as an actual raw pointer. Turns this into a raw pointer, and then we just say convert the pointer types as you like to make it happy. This should be pointing to the correct kind of thing for curl to deal with. So otherwise that seems okay. And then we get to perform it. Curl easy perform with our curl. Like that. And I guess at the end just say curl clean up our curl. So let's see if this FFIs over to curl and performs a web request. How cool is that? Huh? How about www.google.com? Hey! Right. So this is actually like, oops, that's not what I want. This is actually going through my system and it's finding curl when I run cargo build. Now, is it going to be statically linked or dynamically linked? I think by default, Rust will statically link it, but we can check. We can do LDD of target debug curl insane. And we should see libcurl somewhere. Libcurl, there we go. So it looks like it is dynamically linked in this case. So it's essentially saying this thing that we've compiled here, insert, this is, you know, very vague, this is very hand wavy, insert like the code for libcurl at this address, and you can grab the library for it from this location on my system, which, you know, points to a slightly different one there, and so on and so forth. But this here is an actual, like, the curl library that we can use. And we can just pull this in from our Rust and do crazy stuff like this. So your one FFI exercise this week, already has the link set up for you. And the code should be able to discover the library that we've given you. We've given you like a secret C library that does some secret calculations, but we've given you a header file to show you how one would call it. And your job is to write the function definition and then call that with unsafe in your thing. So this might be a good reference in terms of just like playing around with what FFI should look like and roughly how you should do it. But it should only be like a 5 lines of code kind of exercise, not like a huge crazy thing. Cool, but yeah, I think this is just a really fun program in general. Yeah. So I think there's a couple more slides here. So that was what I needed to help me do that. Now, in terms of the parts that sucked about writing that example, I don't like having to like write, and this is true for me. I don't like having to write all this myself, right? Like function blah is this and function blah is that, and generating all these types and stuff. That's annoying. I hate that. Fortunately for you, there is a tool to automatically generate Rust FFI bindings to C and some C++ libraries. That program is called Rust bindgen. So if you don't like doing that manually, then probably a program like Rust bindgen is what you're looking for there. And it can just take a C header file and spit out, here's the Rust code to talk to this C library, which is awesome. You can also do this from the other direction, which is if you write Rust code that you want people to be able to call from, say, C or C++, a project called cbindgen will generate C or C++ header files in order to talk to Rust libraries, which expose an API to be called. So that's sort of like the other direction around. We were in Rust code calling C, but if you're in C and wanting to call Rust code, then you can do that the other way and automatically generate all that yourself as well. So that's pretty cool. We were thinking of getting you to do this, but that would also involve students having to write C or C++, which we don't really want to force you to do. So we don't have any assessed exercises or anything on you writing that. Next thing that sucked. I don't want to use cbindgen. I don't want to have to do all this work and figure out how this program works. I just want to be able to use a C library. Well, the good news is someone probably already has used cbindgen or bindgen in our case. These are generally known as Rust bindings. And so, for example, in the case of curl, there's a crate called curl sys, right? And this is literally just a crate that sort of generates those FFI bindings so your Rust program can talk to curl, which is awesome. So we should be able to see things like functions. What functions are where? Curl easy init, curl easy set opt, curl easy init is here, curl easy set opt is there, perform is here, and cleanup is here. And like, here's the extern C functions all just sort of laid out like this. And so you'll be able to call those and use their types. So for almost every like popular C, maybe like C++ library, someone's probably already done the work in generating those Rust bindings. Another popular project that came to my mind was SQLite, which lets you do a SQL database through a file through a program called SQLite. And here's like SQLite sys. Someone's made bindings for it already, which is pretty handy. Next thing that sucks. I don't want to use the C types everywhere. Like it's annoying having to convert, like use C strings and raw pointers and all that pain. Like even if I'm using someone else's bindings, right? Like curl sys here, these functions are still in terms of like raw pointers, raw pointer, C strings, that kind of stuff. That can be annoying, right? You don't generally want to do that if it's going to be avoided. You have to do it eventually, because eventually you're going to have to talk to the library if you want to talk to it, and you're going to have to speak its language. But again, if you don't want to use those C types everywhere, you could just make an abstraction that takes like, stuff in Rust land and then does the unsafe, has an unsafe implementation that goes to talk to the C, creating a safe abstraction on top. And before here we had curl sys and SQLite 3 sys. How about curl and SQLite? So if we look at these crates, curl and SQLite, we'll see that these basically make like legit Rust types that make it easy to use that C library from within Rust. But at the end of the day, like it's going to be powered by libcurl, and it's going to have to use the curl sys crate. So this crate links to curl sys, which is responsible for linking to the libcurl library. And if we look at probably how, say, let's look for like perform, or what do they call it? Yeah, perform. That would be here. We're probably going to see that it ends up calling self do perform, self inner perform. Okay, well, like, yeah, they've made it really fun for us naturally. I'll see if an easy goes to an easy 2. Screw you. Easy 2. Does this have an easy 3 inside it? There is this. Right, here we go. That's what I was looking for. Eventually you'll see it. This thing here is actually using those raw bindings from curl sys. But like, it's made a nice abstraction on top of that, so we don't, like, every person doesn't have to end up calling curl easy perform with the raw pointers and stuff like that. So that's sort of like the last layer here generally. Once you're at that point, you're all the way back in Rust, but you're using things written in completely separate languages, pulling it all into one common program. So FFI is a pretty cool and fun idea. It's very dangerous, because as soon as you're leaving the blessed land of Rust, all these safety invariants and all that can easily be absolutely destroyed. And so we want to be careful with FFI. It's an unsafe operation by its nature, but it allows us, you know, lots of things that wouldn't otherwise be possible, like talking to a lot of existing libraries, and it makes it possible to integrate Rust into an existing C or C++ code base, you know, over time, which is what things like Rust was originally being developed for something called Servo, which is a browser engine, which I believe Firefox actually uses these days. It was like I want to say something like a CSS engine or something like that, that was heavily parallel, because it's really funny. It was written in C++ originally, and they kept wanting to parallelize it, right? Take advantage of concurrency and thread safety and all that, threading and all that, to make it run a lot faster. And every time they tried to parallelize their C++, they always got these horrible errors, and like, people were reporting bugs and crashes and all this, and they could just never do it because it was so hard to write that C++ correctly. And then they were like, what about, like, we use this sort of, like, Firefox is under a company called Mozilla. The Rust project was also being incubated in a certain sense by Mozilla, and they were like, let's develop Servo and Rust sort of hand in hand. And so Servo informed Rust a lot, and Rust was, you know, a big chunk of Rust was created to create the Servo project, which is pretty interesting. How does versioning work with Rust wrappers over C libraries like curl? That's a great question. I don't, like, it's going to be different for every individual crate, you know, for how people do it. But you can see that this crate in particular, curl sys, have opted to create, this looks like, you know, probably it's like 0.4.59 is maybe like this crate's version, and it's compatible with curl 7.86.0 probably. And like, oh, maybe I need to use this one if I want to use curl 7.82.0. But it's really, I guess it's probably down to what you do. We can see here SQLite is not necessarily the exact same thing. But usually libraries are pretty careful with their API and how they affect their API over time through updates and stuff like that. Usually to remain backwards compatible and to not break existing cases. So, you know, your bindings, in a sense, get to take advantage of people taking that care most of the time. Yeah, cool. Good question. All right. Let's call the lecture there. End of lecture. And I'm happy, again, as usual, to field questions for as long as you want. And then once I switch off the lecture, I'm going to be going back to that Vec code and try and figure out where that undefined behavior is coming from. But yeah, any questions that you've got, I am very happy to hear them. For as long as you've got them, basically. My sample implementation doesn't have the same undefined behavior. Cargo nightly Miri run. Yeah, that's interesting. Oh, so I've got one version that does work and one version that doesn't work. Oh, that like has undefined behavior. That's quite interesting. Where are we here? Is there something like micro Rust for running Rust code on embedded devices without stuff like malloc, etc.? Yeah, Rust is built to do that, which is pretty cool. So that's sort of like a default feature of like Rust the language, as opposed to sort of having to like fork the language or make extra language libraries and stuff to like specifically support embedded and platforms without allocation and stuff like that. And the general way that you would go through doing something like this is using something called no-stud. So Rust, by default, supports writing Rust code that in like a headless mode, essentially running without the standard library. And in fact, you can even like pick and choose bits of the standard library that you'd like. So when you go no-stud, right? No standard library. By default, all you get access to is the core library, which is essentially like the standard library, but way more minimal. And it can be like, you can take away everything that does heap allocation, no concurrency, no IO, that kind of thing. So core tries to be able to run hopefully any way you want. If you're in a place that, you know, you're working in say like OS code where a standard library is absolutely not going to work for you, right? Like needing a file system and that sort of stuff when you might be the one writing the file system, but maybe you do have things like allocation, like heap allocation and stuff like that. You can bring in the core library and also the allocation library, which pulls in things like string and vec and stuff like that and box for you, which is pretty handy. But even in this case, like core relies on very little, like mem copy, mem compares, mem set, strlen, Rust, like panicking stuff, and this personality. Like it relies on very little, but you can also still even run Rust without core, which is called Rust no core, unsurprisingly. And this, why is this tracking Rust? There is a where is it? Rust no core blog. Someone wrote a blog post on no core oxidizing the technical interview. Yeah, here we go. This is what I was thinking of. Where you can even go, take out the core library and implement like the really basic stuff of Rust yourself, which is pretty cool. And this is made by Michael Gottozzi, who's also a very knowledgeable member of the Rust community who you should similarly follow on Twitter if you're still using Twitter. Again, I need to catch up on all that, obviously. But Rust is very flexible in allowing you to only pick and choose the bits you want, which means you can, in general, hopefully run Rust like almost anywhere over time. So yeah, it's definitely a pretty cool thing. Cool. Any other questions before I try and delve a little bit into what the heck is going on here? That seems fine. Yep, write the value. Yep, pop. That seems about right. Yeah, that really shouldn't be any difference, but I'll just do it anyway. So that's fine. Get. Oh, that's the problem. That's what I've done. Oh, yes, that is absolutely undefined behavior. Oh, okay, I figured it out. Okay, cool. I can just address it at the end of the lecture now. Okay, that's the undefined behavior. Right. So this here, no, not this one. Pop is perfectly safe to return an owned T because it's actually like effectively taking it out of the Vec and giving you ownership of it. Get can be called like time and time again on repeat, right? You can go get the fourth thing, get the fourth thing, get the fourth thing, and you should always be expecting to get something back, but probably not ownership, right? Probably not like an owned value of that T. That's like, otherwise you call get 3 times and you now have 3 copies of that same owned value. So this is absolutely undefined behavior. It should not be this at all. Instead, get should return a borrow. Ah, yes, get should return a borrow. And then this pointer read, I'm going to replace this with dereference me the thing at that pointer, and then like borrow that inline there. Right. So this safety was not really same as above, and it is safe to borrow since we have a since it is tied to the lifetime of the borrow oneself. So that's fine. And this is same as above, and it is fine to take ownership of the T because we are effectively removing it from the Vec by decrementing the size. Right, okay, yes, I was just missing that argument in its entirety, and now I bet Miri is happy with it. Miri test. Hey, how about that? Oops. And it's still testing everything. Yeah, great. That's it. Hopefully that makes sense as to why that was undefined behavior. This is just like, nothing's really going to stop you from doing that if you're going through raw pointers, because Rust won't make really a ton of assumptions about it. But if you screw it up, it's still going to, like, Miri will still tell you, hey, that's undefined behavior. It's probably not going to do the right thing. So that's great that we've managed to see that one. And hopefully the fix here makes sense. Cool. Then that's really it. I don't even have to do this after the lecture. That's great. So any last questions? We haven't seen anything in the chat in the last few minutes, so it seems like people are generally happy. I hope. Oh, cool. I'm glad we managed to fix that. I'll push this up to Git. Nope, not this. Yes, that. Lex 16 curl plus vec plus curl. So that's going up there now, so that should all be accessible to you. So you can play around with that code and yeah, mess around with it. Otherwise, it seems like we don't have any other questions. So thank you everyone for coming. Hopefully this was a bit of a fun lecture, doing a bit of crazy stuff at times. And yeah, thank you all for coming. And congrats, we're through our content. Yeah. So I guess week 10 is still up in the air in terms of what we might want to do in the lectures. As a default, things like revision, like going back over some bits and pieces that people weren't super confident in, is something we absolutely can do. Other interesting topics that we can like rule out of assessment, but like I'm interested in this thing just out of interest and we'd like to, you know, play around with that stuff, is perfectly on the table as well. So if you've got any thoughts for what you'd like to see, revision or other interesting topics or otherwise, just throw them on the course forum, you know, throw in a new topic with any ideas that you have, and we'll figure it out. It would also be cool to see how we can use FI to call Rust code from C. All right, great. That's a nice idea. If you like, actually, let me make a thread now. That seems like a sensible thing to do. Lectures, week 10, lecture topic ideas. Comment below with any revision topics or new non-accessible topics that you would like to see covered during our currently relatively free week 10 lectures. Yeah, that seems good. Yep, go away. Non-accessible. Yeah, I'm pretty sure I got that one right. Create topic. All right. post your ideas here. If you want to see FFI to call Rust code from C, just leave a comment here if you're able to, Patrick, just so people can like heart it and if they like that idea. But post your ideas in here and we'll aggregate them and figure out what to do for week 10. So great. Thank you, everyone. And I'll see you all. I'll see some of you in the workshops this week, and I'll see the rest of you in the lectures in week 10. All right. Bye-bye now, and see you later this week.